Okay, we'll get started here, and I guess before I begin today's content, I just want to check, see how you guys are doing. Are there any questions or concerns? So a few questions on Piazza. I hope I was able to, I don't know, help. But everything's going okay? No? Maybe? Okay. All right. Well, it's the fourth week in our summer session, and so we're gonna start to make the transition away from learning things in R to learning computational statistics. Okay. And so at the beginning of the course, I said computational statistics. The practice of that is it's kind of this broad subject, but a large part of it is using the computer and these computationally intensive methods or numeric methods to solve statistical problems. Okay, and so rather than trying to maybe use an analytic approach to solving certain problems using equations and formulas and things of that nature, we can try to use the computer to estimate and get a very good estimate of the answer that we're looking for. Okay, or actually, this is from an old class, so we'll cut that out. But a large part of this depends on our understanding of the machine representation of numbers. Okay, that's going to play a large part in getting computational statistics to work. And so we'll have to go through a discussion of this, and it can feel a bit dry at times, but I think it's worth noting. So, one thing you can do in R is you can just type in dot capital machine. Okay, and it's gonna spit out a bunch of stuff here. Okay, and this is information that depends on your computer system. Okay, so if you have a PC, if you have a Mac, you might get slightly different things here. I think most of our machines are Intel-based machines, so a lot of it will kind of will work similarly. Okay, but it's important to note that we are accustomed to using numbers in the decimal system, right? Decimal, so everything's base 10. When you go one spot behind the decimal point, it's the tenths place, and then another spot is the hundredths place, and things like that. Whereas in the computer, just over time, we have the computers today generally use a binary system. Okay, and there's nothing wrong with binary, and there's nothing wrong with decimal. It's just they're different, and so you're gonna run into some issues where you're trying to express decimal numbers in a binary system. And it's okay when you are talking about integers and things of that nature, but when you start dealing with floating point numbers, so fractions, then we can run into issues. Okay, and so with binaries, we have an on-off indicator called a bit. All right, and then a lot of times if we group 8 of those bits together, we have a byte. Okay, and we associate 1 with on and 0 with off, and that doesn't really matter. And this is all happening at a fundamental level inside the computer. So R has no control over how numbers are represented inside your system. This is happening at a much deeper level. Okay, and so we'll have a fixed number of bytes, and then and oftentimes our machine will have a certain number of bits that we can work with, and so usually 32 bits or 64 bits. Probably most of our machines are 64-bit systems these days. Okay, and we have a few ways to represent integers. Okay, and you can check by looking at dot machine. You can see let's see, integer max. This is the largest integer that my machine can represent. Okay, anything larger than this, the computer can't represent that. Okay, so if I need an integer bigger than this value, I'm out of luck. Okay, at least with the number of bits that my computer uses. So the way integers can be represented in a machine, and this is it's different from system to system, is that there's the sign and magnitude scheme. Okay, and this is probably if you told a person, I want you to come up with a binary system, a way to represent numbers of binary, I think the default, the way we think, would probably go with sign and magnitude, because this is probably most similar to our decimal system. Okay, I'm assuming you guys know how to look at numbers in binary. So if we had an 8-bit number, okay, we could represent something where the first bit is either going to be a plus or minus, okay, and then you have 7 remaining bits to represent the number. So in this case, I would have a negative number, and then 0, 1, 0, 0, 1, 0, 1, okay? And then so because this is in the 5th spot, this is in the 2nd, and this is in the 0th spot, okay? This number would be represented as negative 37, okay? Is that all right with this line right here?
Is that the 6th spot?
Huh? It's the 6th spot, okay? But remember, the first spot, the ones place in the decimal system, is 10 to the 0. Okay, and then the next spot over is 10 to the 1. So it is the 6th from the right, but this is 2 to the 0. This second spot would be 2 to the 1, 2 to the 2. So this would be 2 to the 5th. Sorry. Okay, and then it goes up to 2 to the 6th, and then this last one represents whether it's positive or negative. Okay, so we have 2 to the 5th, 2 to the 2nd, and 2 to the 0, representing negative 37 here. Okay, and then so the largest number we can represent would be basically having everything ones, okay, which would be one less than 2 to the 8, right? I mean, sorry, 2 to the 7. So this would be 2 to the 7 minus 1, 127, and then the smallest number we can represent would be negative 127 in this case. Okay, and so we have a total of 256 numbers that can be represented. Okay, except we're going to have 2 representations of 0. You have positive 0 and negative 0. Okay, or basically everything is 0 except you've got a positive or a negative in there, and that's fine. That's one of the disadvantage. Okay, in the biased scheme basically is like, well, it's a waste to have 2 representations of 0. I don't want a negative 0. Okay, I just want 1 representation of 0, and so basically you take your number, okay, and then you just subtract 255 from it. Okay, and so that's what we have. Okay, and so in this case you can have large numbers or small numbers and things of this nature. So in this case, this number would be represented that way. And in the complement scheme, okay, positive numbers are represented in the regular way, okay, and then negative numbers are represented such that it's, how much does it take to add up to a certain value, okay? And so this one seems the most strange, except there's a few computational advantages. Okay, you don't have to worry about all of the inner workings here. Okay, just know that that the computer does this at a machine level that's kind of out of our control. But having an understanding of how numbers are represented inside the machine will help us understand, why we might run into certain problems in the future. Okay, so let's take a look. So as far as integers go, the computer can handle integers pretty well, and we don't generally run into problems unless you're trying to use an integer for a number larger than your integer max on the machine. Okay, so this is the largest integer value. So you can do dot machine integer dot max, and that would be the largest that you can represent. Okay. All right. When we have decimal numbers, okay. So it says decimal numbers can be represented in scientific notation. So this is just one way to think of it. So we can think of the number 1200 as 1.2 times 10 to the third, okay? Or in R, we would write 1.2 E3. And then, so I don't have this written here, but in decimal notation, again, the spot behind the decimal is the tenths place. So it's basically 1 over 10 to the negative 1. The spot behind the behind that would be 1 over 10 to the negative 2. And in binary, you basically have b sub 0, the decimal place, b1, b2, b3. Okay, and so it's similar to this, except it's all binary, and so you have this represented times 2 to the m. Okay. And then so this spot, b sub 1, represents the 1/2 place. The next spot represents the 1/4 place. The third spot would be the 1/8 place, so on and so forth. Okay? And then you multiply that by the exponent 2 to the m. And so in this case, we have 8 bytes used to store the floating point numbers. Okay, 1 bit is used for the sign, and then the other 52 of the bits. So 8 bytes is 64 bits, right? So you have 1 bit for the sign, 52 for the mantissa, which would be the all the B0s, B1, B2, all the way up to B to the sub 51, I guess, and then 11 bits for the exponent. Okay. And then the biased scheme is used to represent the exponent, so that can go from negative 1023 to positive 1024. And then the 52 bits go from B1 to B2, or B52, I'm sorry, and where the value of B0 depends on the mantissa. Okay, so whether this is a 0 or 1. All right. Okay, so if we have the mantissa being the smallest number it can be, then B0 will be a 0. Okay. All right. So this is as the smallest value that we can have, and so the value 0 is represented by having the mantissa equal to negative 1023 and all of the bits equal to 0. Okay, and then we can get values actually smaller than 2 times 10 to the negative 23 by leaving b0 equal to 0 and then having and then setting the other digits. So you can think of this as kind of like if you had to represent a number. Let me pull up my text. So let's say we were using a decimal system, okay, and it was like you had you can represent 8 numbers, and then you had some kind of e to the m power here. You might think that the smallest, like let's say the smallest number you can go would be e to the negative 8. You might think that the smallest number you can represent would be 1e to the negative 8, but that's actually not true. You can actually, because 1e to the negative 8 would be something like this. You can actually get much smaller numbers by using something like 0.1 times e to the negative 8, okay? And this would be the equivalent of e to the negative 9, right? And you can have a bunch more zeros, and so this would actually be the smallest number that can be represented. And this would be, you know, the equivalent of 1 times e to the negative 15 or something like that. Okay, so if you leave this first number as a 0, then you can get quite small numbers by leaving by everything else. So it's useful in that case, all right? But then so you might be able to get really small numbers, except that only works when it's close to 0, okay? Whereas as soon as you put a value in the front here, okay, so let's say we could have 7 digits behind the decimal place, okay, and then we have an exponent that can go up to something like this, e to the 0. Once you have a number up here, you can only get up to kind of up to the 7th decimal place behind the 1. All right, does that make sense? So whereas, you know, if I leave a 0 up in the front, I can get something very small. So I can, if I set this e to the negative 8, this is essentially, it feels like I have, you know, 1 e to the negative 15. It feels like I can represent really tiny numbers, which I can, okay? But if I'm forced to keep a 1 here or something in front of the decimal place, I no longer can represent numbers on this order of magnitude. I'm limited to getting numbers out. This would be the smallest kind of difference that I can establish. So I can detect the difference between this and this, but I can't detect the difference, you know, if I wanted to add something like this value to here, I won't be able to do it. Okay. Yes.
For the Mantisa, we're multiplying all of these.
The
BIs we're multiplying all of them.
No, they're I'm sorry. What?
Like with the x equals b naught d1.
This? Yeah, no. You're not multiplying them. It's just like representing something in decimal notation. Okay, so if like when I say like 1 point, I'm not multiplying 2 times 3 times 4 times 5 times 6. This is 1 plus 2 times 1/10 plus 3 times 1/100th plus 4 times 1/1000th and so on and so forth. Okay, and it's basically the same, except in binary it's going to be something like, and this would be 1 times 2 to the 0, okay, plus 0 times 2 to the negative 1, so 0 halves, and then 1 times 2 to the negative 2, so plus 1/4, plus 1/8, plus 0/16, plus 1/32, things like that, okay? Whereas over here, we're talking about tenths, hundredths, thousandths, 10,000ths, hundredths, thousandths. Here we're talking about halves, quarters, eighths, 16ths, 32nds. Okay, so we're not multiplying them, okay? And it wouldn't make sense to multiply these because these are all just ones and zeros, right? So they're placeholders in the halves, quarters, and eighths places. Okay, and so we're representing all of this with our 52 bits, okay? And then we have an exponent to kind of to tell us these things, okay? So if you have you know, any other number other than negative 1023, then you've got the first placeholder equal to 1. Okay? And then if you have the exponent equal to 1024, and then everything is zeroed out, then R understands that as positive infinity or negative infinity. Okay? And then if you have a 1024 here and then something here, between one of the bits is not equal to 0, then that's going to be not a number. Okay. So again, the smallest number we can represent would be 2 to the negative 1074. All right, and that is by having in the binary notation, basically we have this maxed out to 1023, and then I'm going to have zeros all the way up basically to the 51st digit, and then the very last one is a 1. Okay, and then so this would be equivalent to 2 to the negative 1074. That, so I can represent that here. Okay, but if I try to do anything smaller than that, R says I don't understand what you're trying to do here. Okay, so the smallest number I can do is 2 times 10 to the negative 1074. Okay, and R can turn that into kind of an approximate decimal equivalent. But anything smaller than that, it doesn't work. Okay, because R is going to say, well, that's like 0. Okay, and then the largest number is basically, I'm going to have everything filled out to 1s. Okay, and E would be 1024, right? Okay, and then so that is this is our real max. This is something on this order times 10 to the 308, and then we can see that by looking at where is so we can see double x min, which is the smallest value that we can represent when we see that right here. Okay, and then the max. This is kind of our real max here. Okay. This value right here, this is known as real max. This is the largest number that we can represent on our computers. Okay, in kind of this double precision. Okay, so remember, double is kind of the default value when we write in numbers. So if I say 45 and R says it's 45, and I ask, type of 45, it's double. So this is kind of the default way R handles numbers in the thing. Okay. Okay, and like I said, we have, but if you have a number here, if you put in a 1000, okay, the smallest number that you can distinguish between two things here, between this number and this number, this is known as our machine epsilon, okay, and that is 2 to the negative 52, right? Because we've got 52 bits for the mantissa. Basically, we can distinguish when the mantissa changes from 1 to 0 here, okay, at the 52nd place. Okay, so so while I can express really tiny numbers, okay, basically my double min, I can't, as far as distinguishing one number from another, the smallest I can get is 52 bits out from the decimal place, or not decimal place, I guess the binary place that separates it out. Okay, and so that's machine epsilon. Okay, all right, and so so here are a few things, and I showed some of these. So again, the smallest number we can have is 2 to the negative 1074. Okay, 1020, 23 plus basically 51 spots out. So we can say that this is not equal to 0, but and we can say, is that equal to 0? And it's going to say false. Okay, but if I put in 1075, R does not distinguish this from 0. This is equivalent to 0 in R's mind. Okay. I can ask, what is what is this equal to? And that's equal to 0. If I divide by 1074, that's also equal to infinity. So these are these all get kind of maxed out here. Sorry, let me go to here. This is a very big number, and I can if I do 2 to the 1024, I think this becomes infinity. 2 raised to the 1024 is infinity, but 2 raised to the 1023 is not. And I can also add 2 to the 1022, okay? And we can get numbers approaching real max. 2 raised to the 1021, okay? So these get closer and closer to my real max, which is represented by dot machine dot $, double max. Okay, so that's the biggest number I can represent. And if I try to like if I add 1022 twice, that exceeds the real max. So I can't. Let's see. I'd have to do plus 2 raised to the 1020 to, I don't know, let's say 1,000. Let me see if we can get this all together. Okay, so here's a number that approaches real max, right? Because I've added up 1023, 1022, 1021. Okay, and we can't, as far as showing 8 decimal places, our default setting, we don't see a difference here. Okay. But again, this idea of machine epsilon is very very important here. Okay, so let's go back to here. So because the smallest value that we can distinguish between one number and another is 2 to the negative 52. Okay, so let's just see what happens. All right, so here I'm going to have x is equal. So I'm going to say x is equal to 1. Okay, and if I can add plus 2 to the negative 52 here. Okay, and I can do x minus 1 and see what we get, and we get this small number. So we can actually distinguish between 1 and 1 plus 2 to the negative 52. Okay, but if I say x is 1 plus 2 to the negative 53, and I ask what is x minus 1 now, it can't distinguish between these two things. Okay, and so this is known as our machine epsilon. It's just our computer can't see the difference between these two values. Okay, so of course mathematically we know that these two things are not equal to each other, but as far as the computer goes, they are exactly the same. Okay, because this thing, and it might be confusing because the computer can represent this. Okay, the computer can say, oh yeah, I've got that number. Okay, but then when you try to add a number of this magnitude or smaller to some other number like 1, okay, the computer can't keep track of it. It's lost space in its, you can think of, you've got this form where you've got a limited number of digits to write down, and you just can't keep track of that anymore, okay? So and so, you know, there's you can, in R you can do something like options digits equals, you can set it to like something like 22. I think this is the largest number you can have, okay? And so you can see things like when you represent 0.5, it represents 0.5, no problem, okay? But if you have 0.3, the way it stores it in the computer is actually not 0.3 but 0.2999999. Okay, now if you set your options back to its default, which is digits is 7, okay, 0.3 looks at like 0.3, okay? But if you set options digits equals to 22 and you ask for 0.3, you get something like this. Okay, and the reason for this is because it's represented, the computer stores this in binary notation, okay? So for example, so when I'm basically asking for 0.3, I'm asking the computer store this number 3 divided by 10, okay, and store it in binary notation. And when it does that, it's unable to do it perfectly, okay? So for example, if I told you store the number 1/3 in decimal form, okay, the best you can do is 0.333333333, right? And you got to say, like, should I leave this as 3 or should I put it 4? This is wrong, right? So you've got to store it like this, okay? Is this equal to 1/3? No, it's not equal to 1/3. It's close to it, but it's different, okay? And so basically we're asking the computer store 3/10 in binary notation, and the best it can do in after going into binary and then converting it back to decimal is storing it this way, okay? So basically when we ask the computer store 0.3, it's inside the computer, it's going from 0.3 into binary, and then when it spits it back onto this screen, it's taking that binary representation and turning it back into decimal representation. And then so you get something like this, which is very close, but it's not exactly correct, okay? And because of this, you get into weird situations where you might ask, what is 0.1 plus 0.2, okay? We look at this and we go, oh, well, that's easy, that's 0.3. But in the computer, because it's turned 0.1 and 0.2 into binary and then turning them back into decimal, you get something that's a little bit different. Yeah?
So these are just like rounding errors from the conversion?
It's basically rounding errors, okay? The computer's doing the best it can, okay? But it doesn't have an infinite number of spots to store these things, okay? It's got basically 52 placeholders in binary notation, and then so yeah, you get these kind of like these artifacts of rounding, okay? Yeah.
And then is that why, like, when you reduce the precision, like to digits 7, it doesn't have as much of a rounding error? So
Well, okay, so no, the rounding error is there, okay? Like these numbers are stored inside, okay? And then so let me just show you. So I got 0.1 plus 0.2, and I can do a test, right? Is this equal to 0.3? Okay, now we in our minds, of course these two things are equal, but you have to keep in mind R represents these in binary, and then so when we ask, it says no, these two things are not equal. Okay, and this stuff like this can be very frustrating because you're trying to do some kind of computation. You just ask R, am I getting the right number? That I'm expecting to get this number, right? You're doing something, and then maybe just part of your code, you're saying, okay, I want to make sure I'm getting the right number here. And then you'd say like, okay, well, you know, is 0.1 plus 0.2 equal to 0.3? And then when you test for that, R is going to say, nope, they're not equal. And if you're not familiar with what's happening inside the machine, an error like this, or this result, it's not an error, it's just this result can be frustrating because you might not fully understand what's going on. And what's going on is that 0.1 and 0.2 are being converted into binary and then returned back into decimal, and you're getting this, okay? Whereas 0.3, again, it's getting converted into binary and it's being stored this way, and you're getting a different result, okay? And we can turn options digits equal to 7, okay? And we do 0.1 plus 0.1 plus 0.2, and it looks like this, and we can say 0.3 is that, okay? But if we do 0.1 plus 0.2, is that still equal to 0.3? It's still going to give me false, okay? And you can be like, what's going on? And that's because at digits equal to 7, the computer chooses to display only up to 7 digits of precision. Okay, and at 7 digits of precision, 0.1 plus 0.2 is equal to 0.3. And at 7 digits of precision, 0.3, these things, when you round off to 7 decimal places, is equal to 0.3. Okay, but internally, the computer is still storing 52 bits of precision there. Okay, it's stored as a double. It's stored as type double, and so internally, it's stored this way, and it says this is false. Okay, so what are we supposed to do? If you needed to test something like this, what are we supposed to do? Okay, you can use this thing called all equal. Okay, and yeah, so we can see, you know, what's going on here. So we can see, you know, 0.1 plus 0.2 minus 0.3. Okay, so we're getting something like this. Okay, and so we can use something called all equal, and this is basically, instead of using are they equal to each other, using the double equal, you can say 0.1 plus 0.2 is it equal to 0.3, and that returns true. So what is all equal? All equal is a function that tests to see if two objects are nearly equal, and it tries to basically say, okay, my computer has something called machine epsilon, okay, which is the difference between what it can tell and what between one number and another number, and it just tries to see, is it within 1 square root of that. Okay, so basically a much larger factor than what the true machine epsilon is. But it basically says if we're getting something you know, that's very close to each other, we're gonna say it's okay. All right, and so all equal will help cover up for some of the kind of the internal issues, and one way to think of it as is rounding issues. It's really just a storage issue. It's the fact that you're trying to store decimal numbers in binary, and you don't have an infinite number of placeholders, right? Just like storing 1/3 in decimal is not going to give you precise answers, right? And if I said, you know, what's 1/3 times 3? Okay, some of your calculators, most of your modern calculators are smart enough to know this, but some of the older calculators will return something like this. Okay, if we did 1/3 times 3, it would return something like this, and that's basically what we're seeing when we do arithmetic in R here. Okay, is this okay? Are there any questions or issues with this? So I'll to say, just be aware. It's important to, when you're trying to do some numerical methods and some calculations in R, and you're expecting certain numbers, just know that because the way R stores numbers, or the way computers handle numbers, is binary, and we're accustomed to using decimal, there's going to be some issues switching between systems, and the numeric methods you get will not be may not be what you expect. Okay. We also have something called loss of significance or catastrophic cancellation. You can look up loss of significance on Wikipedia. Oh, and I should say this is kind of the standard back up here. This is the standard for how numbers are stored. So if you go to this on Wikipedia for double precision, it shows you how all of these numbers are stored. Okay, we've got the exponent, the fraction, and then the sign. So you got 64 bits, right? And so this is how your numbers are stored. And in 32-bit, it looks like this. So if you have a 64-bit system, this is what's going on. If you got 32-bit system, this is what's going on. And so you know, it talks about all of these issues and stuff. But it's okay. So you know, we have this on the computer. Okay, you can represent something like 1 dot 0.2345678901234567, something like that, okay? And if we ask, what's the difference between this and this, we see that, the difference between here and here, that it's not that big of a deal, okay? Because so it says a floating point representation of this number on a machine keeps about 16 floating point digits, okay? So here's a decimal number with 20 decimal places, okay? And on our machine, it keeps about 16 decimals of precision, okay? And so the difference between this number with 20 decimal places and this number which is stored internally with 16 decimal places, it's not that big of a deal, okay? And so let's say I want to subtract off this number, okay, from this number over here, okay? So basically it's the same number where I'm leaving 7890, okay? And both of these numbers can be represented just fine in if we were to do this mathematically. So mathematically, we would know that this minus this would be a whole bunch of zeros and then 7890, okay? So this is not done in the computer. This is I'm saying this is what we know the answer to be, okay? And the computer can store this 7890. It can store this number just fine, okay? And it would store it as 7.89 times e to the negative 16. The computer can store this, no problem, okay? But if we were to actually do this calculation on R, so the black text means I didn't actually do it. When I actually do the calculation in R, what do I get? I get this number. I don't get 7.89 e to the negative 16. I get 6.66 e to the negative 16. Okay, so what's going on here? The problem is, again, is that we're experiencing this issue of catastrophic cancellation. Basically, we're asking R to keep track of a difference that's smaller than it's normally able to keep track of, okay? So because of the way the numbers are stored, okay, we're trying to basically, if you think of how those two numbers are represented in binary, pretty much almost all of these numbers as far as the mantissa goes, all of these numbers are represented almost identically, okay? And then there's just a small difference with the, I'm sorry, it goes this way. So all of these numbers up here are, and then it's just the kind of the tail end, those numbers are represented differently, okay? And so it's trying to compute the difference between these two numbers, and so it does find those numbers, but because you only have you've got a few bits here, okay, let's say you're trying to represent that difference using kind of like the last 4 or 5 bits, okay, there's only so much precision you can represent with that, and because of that you're getting an answer that's kind of on the same order, but as far as accuracy, it's quite off. I don't know if that makes sense to you guys. Okay, so I guess you gotta if you're trying to find precise differences between numbers, these types of calculations are not going to work. Okay, so or you just have to accept that there are limitations in the manner in which we store values in the computer. Okay, and these are just inherent to doing computation with a machine. Okay, rather than doing it on a piece of paper, if you're using machine, there are limitations. Okay. Okay, why don't we pause here, take a 5-minute break here.